as I only have one board to write on. So, well, I have many books. I have Klaus's book here. I have Marco Manetti's topology book, which I used last time. Of course, I have the Gamelin and Green topology, and also I decided to take a look through my notes from when I took topology, because I think there's some nice examples in here that I should steal. So the examples of my notes are probably from Moncrief's, but I took this course with Dr. Latta of NC State back. Oh, when is this from? 2003. Topology is the same. Anyway, I will begin with a word of prayer. So, Dearly Father, we thank you for this day. Again, Lord, I thank you for the students and for this time we have just to meet together and study your creation. Lord, in your name I pray. Amen. So I'm going to start with trying to define a basis for a topology. I don't know if I did that before, but I'm going to take the definition out of my notes because it seems like it's a good one. I seem to have miscalculated. I should probably actually get a marker right. All right. And because this allows us to generate a bunch of nice examples. So definition, a basis. What's that? Oh, some pathological. No, I mean this is actually a fast path to generating some of those more weird examples. I'll at least say a couple today. A basis for a topology. A basis for a topology is a collection beta of, I'm going to use this symbol instead, script B, of subsets of X such that 1 for each X in X, there exists B in B in the basis, with X in B, and 2, if X is an element of the intersection of two of these, then there exists B3 also in the basis with X in B3, which is, by the way, a subset of B1 intersect B2. Get out! Sorry. There. That felt right. I may have to go tell them to be quiet over there if it gets too rowdy. Let's see here. All right, so this is a basis for a topology. And then furthermore, definition, all right, the topology generated by a basis by basis B is given by, as follows. Here we go. U, a subset of X, is open if and only if for each X in U, there is A, B in the basis with X in B, which is a subset of U. The collection of U is the topology which is generated, right? So this gives us a way of building a topology from some collection of sets, right? This is a basis. So, yeah, I think that the basis is, I mean, essentially by construction open itself. I mean, let's see here. So this X here, that, I mean, okay, there's two different ways we could look at this, okay? X could be a given topological space. Then you could talk about B being a basis for that topological space. So if it's a topological space, there's already a concept of open. So then you could ask the question whether or not the sets in the basis were themselves open, right? And it seems like they don't have to be open, at least from the definition I've stated. But I think that the because you can take singletons, the collection of singletons, and it forms a basis also. Take the collection of singletons and it forms a basis also. Yeah. Right. So I suspect that if we have a topological space, we probably want to look at an open basis. So it's a collection of open sets that satisfies these conditions, then it's a basis. Of course, the singletons would form a basis probably for the discrete topology. Yeah. But what's in blue, I mean, on the other hand, if X was not already, if it wasn't too late to topologize, you know. Oh, it still works. I was afraid that song was too far out. No. So if X doesn't already have a topology which is given, then you could take something that satisfied the criteria of the basis and generate a topology which is basically built over the assumption that whatever's in the basis is open. And that's the topology generated by the basis. And then vice versa. I mean, if you have an open basis that generates the topology, then it's called a basis for the topology. I'm glad I got this out of my system before Sam got here. All right. Now, there is also, in my notes, he's like, if you take R2, an example would be R2 with open disks. Those would give you a basis for the usual Euclidean topology on the plane, for example. Now, a subbasis, all right, what's a subbasis? Let's see if I got it here. Sorry, I'm trying to find an example in here, and we'll have to Another example basis, of course, would be like just open intervals for the real line. Those would form a basis for the reals with the usual topology. All right. Actually, before I even get to subbasis, we can talk about, here's one of the weird examples I promised. We could take X to be the reals and the basis to be the set of the sets of the form A included, B excluded. So if we take this to be the basis for a topology, which, yes, by default means that those sets are declared to be open with respect to that topology, then, X with the topology, generated by beta, whatever you want to use that notation for, this is usually denoted like R sub L or something like that. In other words, this is the real line with the so-called lower limit topology. This is not equivalent to the Euclidean topology, the metric topology on the real line. I mean, there are sets which are open in one which aren't in the other. Well, let's see here. Let's consider, let's see here. If U, a subset of R, is open in standard, the standard topology of the real line, then what does that mean? If we look at U, right, and you pick a point X in there, what can you do? I mean, the standard topology uses open intervals as a basis, right? So any point if it's an open set, then we can pick a point. I mean, there's going to be some kind of like that, right? So open in the standard topological sense. So I guess my question is, all right. So if this is, let me use some color coding here. If that's an open set in the standard topological sense, is it also open in the lower limit topology? Is U open in the lower limit topology? U being this, right? So if it's an element of, tau, let's say R standard, does that imply that U is also in the topology of, the lower limit topology of R? Why or not? So you're saying like that, if that's A, B, then we could fit like, let's say B minus A, how about this, A plus B minus A over 2, comma, A, B, I don't know, I can draw a, why am I worried about why am I fussing about the formulas? I mean, I'm an idiot. You can draw the picture, right? I mean, it's clear that you can stick this around the point as well, right? So then what? I mean, that means that that point x is also an interior point with respect to the lower limit topology, right? Because we can fit an open set around it. I hate to do this. Ahem. 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 Yes. Uh-huh. There's just two of them in there. All right. Sorry, I've ruined the fun. Let's see here. So, yes, x is also an interior point with respect to the lower limit topology, which is to say that, yeah, you know, it is, in fact, if it's open in the metric topology of the real line, it's open in the lower limit topology, right? But how about the other direction? Is every open set in the lower limit topology also open in the real line? Well, no. I mean, these right here are not open in the, you know, in the usual topology, right? That set, that point A is not an interior point, right? There does not exist an open, you know, you can't, that's not an interior point for this set, so therefore this is not open in the metric topology. But by definition, it's open in the lower limit topology. So what this says is open in the metric implies open in the lower limit topology. However, open in the lower limit topology does not imply open necessarily in the metric topology. In other words, what I've explained is that the lower limit topology is finer than the standard topology. On R.
That means that it generates more open sets?
Yes, it has more sets which are considered open. It has everything that's considered open on the reals already, and then some. Right. Okay, so now, interesting, I mean, when I saw this, I was like, well, I mean, first of all, like, this hurt my brain. It was a homework problem for me early in the semester. It just threw me. Because it wasn't just this. It was like asking some questions about, you know, some various questions about something in that. And this lower limit topology is really, it really messes with you, you know, because it's not Euclidean, it's not quite the standard thing. And Minetti actually mentions this topology on page 41, and he has a little footnote about this. Well, he mentions, of course, that it's finer than Euclidean topology, but he also has this footnote. It says, mathematicians do not invent strange-looking topologies just for fun. Robert Sorgenfrey, I'm mispronouncing that horribly, Sorgenfrey, for instance, defined the lower limit topology, in fact, to answer the question of whether the product of paracompact spaces is paracompact. It's not. So like this was invented to serve as an example for a somewhat deep and technical topological question. So, but it's also kind of a nice introductory example. All right. Moving along. There's also a fun, you could also, of course, define the upper limit topology. You could use the basis of, instead of Clopin, you could use opposed sets as your basic open sets. And then there's also a subbasis. What's a subbasis? I should probably write smaller. A subbasis which I use S for topology on set X, is collection of subsets of X whose union is X. The topology generated by S consists of all unions of finite intersections of members of S. So this is a subbasis. Let's see here. Where was I? I don't know if he even has that in Gamelin here. Well, I just didn't see. I didn't see. Maybe it's later. I didn't see it. I didn't see it in his basis section, did it? I don't think it was in there. Where does he eventually talk about subbasis in here? Subbase for topology, page 72. Oh, it's in it's exercise 5. Yeah, there's. It is true, but well, that is unfortunate. Yeah, I guess that's comment. We have to read the exercises in Gamelin to understand topology because a good part of topology is generated in the exercises in this book, right? Which is part of the reason it's a faster read is because it's it's systematically relegated certain things to the exercises, which it may or may not be bad to skip over. Let's see here. I'm trying to find an example where we use the subbasis concept to generate a topology. You guys know one? I have one coming up, so stay tuned. All right, so continuing with my weird topologies. Oh, that's not. I'm sorry. I read too many things before class, and now I can't remember where I found it. Oh, there it is. I found this to be. This is kind of daunting a little bit. So can you guys tell me what is a if I give you set X with a simple ordering, what's that mean? What's it mean to give a simple ordering? It's a partially ordered set? It's a partially ordered, that seems like cheating, but right.
I'm pretty sure the alternative word for that is
Total ordering, totally ordered set. All right, so I'm pretty sure what this means, right, is that if you're given two elements of the set, then what? One has to be less than the other, right? If they're distinct elements. And also that there's, I think, a transitivity, right? So like if A is less than B and B is less than C, then we have that A is less than C, right? I think that's also part of it. Anyway, this does have a technical meaning, which you could look up, all right? But certainly regular less than is an example of a simple ordering. I'll give a less obvious example in just a second, but let me finish this here. So we just have a set with a simple ordering, whatever that means, and suppose it has more than one element, and you can let B be collection of subsets of X, all right, of form number 1, AB, like this, open. So what this would be X and X, such that A is less than X is less than B. Sorry, let me get out of the way. Or 2 of the form A naught B, where A naught is smallest element, if it exists. The smallest element, of course, would be an element A. What makes A naught the smallest element means that A naught is less than X for all X in the set, right? What's that? Oh, okay. All right, I'll allow it. 3, A, B naught, where B naught is biggest element, if it exists, right? Then, guess what? B is a basis that generates the order topology. Or then, let's say this, the topology generated by basis B is called the ordered topology. For X. So I think, for example, if we looked at like non-negative real numbers, I think that the order topology would correspond to the subspace topology. So here's the reals, right? Suppose we're looking at the reals with the standard topology, right? And then you could look at non-negative reals, right? 0 and on. So what is a basis? I mean, you could, what's open in that with respect to the subspace topology is the intersection of the reals and the open ray from 0 to infinity. So like what are open in the reals? Well, we could look at open intervals. Those intersect would give us like half open, including 0, like 0 to A, not included, that kind of thing. And then if our open interval happens to not be over 0, it would just give us a plain old open interval, right? And those are the open sets, the basic open sets in the subspace topology, because those are what you get from intersecting the real. Well, those are what you get from intersecting the non-negative reals with the usual basis of open intervals for the real topology. This is a theorem. If you take a basis for a set for topological space and you intersect the basis with the subspace, it gives you a basis for the subspace topology. That's what I'm using. And my point is that that basis you get for the subspace topology here is nothing more than the order topology on this with respect to the standard ordering of the reals. Because the order topology takes as a basis plain Jane open intervals, which you got, and also these things where there's a smallest element. It exists at 0 in the green. And case 3 is not realized for the non-negative reals. So order topology doesn't have to be weird. It could be something that you're familiar with, right? But it could get weird. So I don't know, I always found this example interesting. That's why I'm showing it. This is so-called lexographic ordering. How does this work? So let's look at a couple of examples. Let's see, 1, 2 versus 2, 3. Or 1, 2 versus 1, 1. So you tell me, which one, what do you think, less than, greater than? I'll tell you, I'm going to tell you these two, and then you can tell me the next, all right? So 1, 2 is less than, I really should make this 2, 1 for maximum effect, all right? So 1, 2 is less than 2, 1. However, 1, 2 is greater than 1, 1. Right, it's like alphabetic ordering, but with numbers. Hence the lexographic ordering. So if we have AB is less than CD, either we have A is less than C, or A is equal to C and B is less than D. Is that right? The way to say it? I know I haven't thought about how to write a general rule for it. I'm an idiot, but anyway, lexographic ordering. And so lexographic ordering is an ordering on R2. So then you can talk about the order topology on R2. So what is the order topology on R2, with respect to the lexographic ordering, You say it'll be a bunch of lines. Let's see here. Here's what I've got. He says, look at and we got to use, you'll have to look at this notation. You'll figure out what it means in just a second here. So since we're using, this also blew my mind when I first saw it, but so this notation is being used in that sense. This means as in this is A and this is B, and maybe CD is over here. So the x coordinate's C and the y coordinate's D. And so this would be what? This would be all points in R cross R such that what? between the points A cross B and C cross D, right? So what would that, all points in are such that what? Good grief. Such that we either would need what? So we're looking, I mean, let me be more precise here. I can write the stupid set builder thing for that.
You need the first term to be less than C and greater than A.
Yeah, I'm trying to think how this would be like x, like the x cross y such that what?
I think X has to be greater than A and less than C.
So A less than x less than C,
Or A can be less than or equal to X.
or A can be,
No, I mean, like, in that first one, it should be A less than or equal to X. And then you'll have to put another condition on X as well. Because X and A could be equal to one another, but Y could be greater than B, and it would still be in between them.
I'm not disputing, I'm just having trouble parsing what you're saying. Let's see here. So what should I write?
So X should be greater than or equal to A. And also, yeah, it should be less than or equal to C.
All right. And then Y is complicated, right?
Y is going to be complicated because it can be whatever you want as long as X is greater than A and less than C. But when X is equivalent to A or equivalent to C, then Y is going to matter.
Okay, so when, I'll put that in red. When X equals to A, need what?
Y is greater than B and less than B, or when it's equal to A.
When X is equal to A, Y has to be between.
It's just greater than B.
Y is greater than B, okay. When X equals to C, need what?
Just that Y is less than B.
Y is less than B. All right.
Then D there. Instead of
Oh, D, not, yeah, sorry. Okay, so let's focus on the red part first. That's when X equals to A. We need what? We have Y greater than B, right? So pretty much that's like this forever and ever up, right? And the other one, X equals to C, Y less than D, right? So that's like this forever and ever down, right? And then as Kang was telling us, lines, right? Unrestricted Y in between those. Forever and ever and ever. That's all she wrote, you know?
So you end up with this space that contains part of its boundary on those two lines going up and down there.
You said a space that contains part of its boundary going up and down there. That is such a Euclidean thing of you to say. That's an open set. And then the topology generated by that is, I mean, then you take what? That's a basis, so you take unions of those to get other open sets. Obviously, this is not the usual topology in the plane, right? I think this qualifies as a weird topology, right? Now, if you're asking me what the application is of this topology, I have no idea. I think the main application is to confuse topology students. So there is. What would you? Not every subspace of an ordered topology is an ordered topology.
So the notion of subspace topology and order topology is not.
Oh, so you're in Moncrief, he makes the point that if we try to let the ordered topology concept descend to a subspace, it breaks. And this example breaks the idea of restricting the order notion to a subspace. Huh. Okay. I have warned that there is more to learn in Moncrief, right? I mean, that's true. But you guys will be fine, of course, if you do the homework in here. I mean, you know, half of the homework. Okay, now, next up, product topology. So if we have, you'll have to remember this because, you know, we still haven't quite gotten to a subbasis, have we? So, all right. This is yet another way of, what I've just shared with you generates a stupid number of really weird examples already. And don't forget, we've got metric topologies to play with, right? But the product topology is if we, you know, definition, let's say if X and Y are topological spaces, with topologies tau x and tau ty respective, then the Cartesian product of x and y has topology called, let's say has product topology. Defined by basis U cross V, where, so it's these things. Let me say this, such that U is in T, the topology for X, and V is in the topology for Y. Right. The way my notes have attacked this, it makes you wonder, is there another definition for product topology beyond, is there a different definition for product topology in which we could prove the theorem that this is a basis for that topology? Like, is there a different way of defining the product topology than to say that this is a basis? Let's see how the product topology is defined in Gamelin. Now, I should warn you, there's something devious that happens when you go from finite products to infinite products. There becomes a distinction between what's called the box and the product topology. But we're in the finite case, so that's need not concern us. Finite products 91. Finite product spaces. He says, this is on page 91. Let x1 through xn be topological spaces. The product topology and their Cartesian product, x1 through xn, is the topology for which a base of open sets is given by, oh man, it's the definition that I just gave. Actually, that's not a, well, Right. Theorem 10.1, let X be the product of topological spaces x1 through xn, and let pi j be the projection of x onto xj. The product topology for X is the smallest topology for which each of the projections pi sub j become continuous. Theorem 10.1 could be used as an alternate, and that's another contender for a definition for the product topology. You could define it in terms of continuity of the projection maps. But anyway, that's just a thought. Let's look at the projection maps, okay? What are the projection maps? Pi 1, x cross y to x, and we also have pi 2, which goes x cross y to y. And I bet you can tell me what the definition is of these guys. What's pi 1 of xy? Little xy. And what's pi 2 of little xy equal to? Yeah, just x, right? And that was the other one? Oh, y, yeah. Now claim that these are continuous. These are continuous functions, right? Here he's got something about the inverse images, the intersection of inverse images under these projection maps, giving an open rectangle. It's open in the product topology, and we've built the basic open rectangle. We found the subbasis. I don't know why. My notes have let me down here. Oh, here it is. A subbasis for the product topology. That's what I was getting to. Okay. Let's look at that. That actually gives us an example of a subbasis. All right. So to understand that subbasis, we have to look at the inverse image of. Well, goodness, man, that umbilicus is slippery. I'm kind of debating here. Partly I want to prove. I kind of want to prove these are continuous maps. I think that'd be a good exercise for us at this point. So let's take a step away from my notes and just see if we can prove that. How would we prove that, say, pi 1 was a continuous map? What do we need to show? Oh, that the inverse does the same. Now that would make it a homeomorphism. And I think that might not be true. So we want to claim this is continuous. Now whenever you talk about continuity, it's with respect to a definition of topology, right? Because it says, like you were saying, the inverse image of an open set should be open, right? So we need to show that the inverse image of an open set is open. All right, let U be an element of the topology on X, right? In other words, it's open, right? And consider pi 1 inverse of U. What's that equal to? That's the set of points X and Y such that what? And not, oh yeah, I got the pi 1. I thought I dropped my 1 for a second there. Such that what? Pi 1 is what? Pi 1 of xy is an element of what? Is what? Oh, U, right. So this is what we mean by inverse image, right? It's the set of points in the domain that map into U. What is that? Oh, so that, yeah, this is, okay, so this, you're saying this is just the condition X is in U. Y is free, right? Y is completely free. X ranges over all of U. So as a set, what we're looking at here is nothing more than U Cartesian product with all of Y. Why is that open? It's in the basis. Ah, do you agree, Emily? What do you think? Is that in the basis? Do you agree with Kang? Why is that in the basis? What does it take for it to be in the basis of the product topology? I'll do the easy part. This has to be in the topology of X, right? Indeed, that was the definition of the basis, yeah. Why is Y in the topology of Y? What is a topology? It contains the empty set, the whole set. Right? So the topology of Y has to contain all of Y. And so we're looking at the Cartesian product of open sets, which is by definition in the product topology open. Therefore, the projection map is continuous with respect to the product topology. And the proof of 2 is almost the same, right? But we can kind of make a heuristic picture of what's going on, right? You could look at it something like this. This is the Y space. This is the X space, right? And you could kind of make a formal picture of this being U, right? And this being V, right? And if you look at pi 1 inverse of U, you've got U cross Y. What is that in this picture? In this picture, U cross Y is a vertical strip, right? It's like this. And in this picture, we could think of, the pi inverse. So this, again, is pi inverse of U. And likewise, pi inverse of V, pi 2 inverse of V, rather. Would be sort of a horizontal strip, right? Like that. So these are both what? We're just explaining that these are both open sets in the product topology, right? So their intersection is open, right? And here's the theorem that I have written in my notes. We can form a subbasis for the product topology on X cross Y to be, it's just things like this. These vertical and horizontal strips form a subbasis. So like a possible subbasis for the product topology. So we could use S equal to things of the form like pi 1 inverse of U, such that U is in the X topology, unioned with pi 2 inverse of V, such that V is in the Y topology. This forms a subbasis for the product topology, because the union of these strips gives everything, and that's all it takes to be a subbasis. the topology generated by that subbasis is formed by what? Unions of finite intersections of the subbasis elements. So finite intersections of these strips give you rectangles. I mean, for our heuristic picture, they give you, yeah, but they give you rectangles, and those, of course, actually are of the form U cross V, which is the basis, yeah. So anyway, that's a kind of non-trivial and very abstract example of the subbasis, but there it is. I'm just trying to take a few minutes to talk about these things with you because I found them to be kind of like, I read it in the book and it just kind of like just goes right through me. I don't, unless I have somebody talk at me about it. Now, what I want to do now is change gears a bit and be a little bit more, let's see here. So where we're going to, I have said some words about basis for topology. There's a section on separation axioms and compactness and connectedness. I think up next I have compact and connectedness. I don't know, did I have separation on the schedule now, or that was later? I can't remember. I kind of don't want to talk about separation at the moment. That's a little bit harder discussion.
I don't even see separation. Oh wait, separation is on Monday.
On Monday, okay. We'll save it for then. So separation is, the topic of separation, like, is a difficult topic, which mathematicians wrestled with over a period of decades to really come to this nuanced and scaffolded understanding of different separation ideas for topological spaces. Can you separate points? Can you separate a point from a closed set? Can you separate two sets from each other? And there's like this T1, T2, T3, and T4. There's this various sort of this echelon of different kinds of separation. The most important one is the notion of Hausdorff. All right, so we'll talk about that Monday mostly. And I'll mention the other separation ideas in passing. If you had a graduate course in topology 20 years ago or something, maybe 40 years ago, it might have made a very big deal of these separation axioms. Maybe they still do. I don't know. No, it's not controversial. It's just that you would spend a lot of time and energy proving all of these various careful distinctions between T1 versus T2 versus T3 versus T4 spaces.
Oh, so they did have
Well,
a system of like the more rigorous system that we have.
they were still, I think the previous generation was just coming to terms with the fact that these were distinctions that could be made. And it actually takes a lot of effort to generate examples to illustrate the distinction between these terms. And that's where a lot of the time would have been spent, just generating these somewhat strange examples which illustrate the distinction in topological terms, the T1 versus T2. Now, what I want to do for now, though, in the time that we have left, is talk about something a little bit there's actually some beautiful formulas in Manetti's book concerning homeomorphism. So let's talk about homeomorphism. I mean, this is ultimately the goal of topology, is to talk about homeomorphism. Have I told you guys what homeomorphism is yet? Homeomorphism. So if we have a function f, which goes from x to y, where x and y are topological spaces, and f is a bijection, right? In other words, f inverse exists, right? So f and f, it's a bijection. And if in addition, f is continuous, and f inverse is continuous, you could also say that f is bicontinuous, all right? Then f is said to be a homeomorphism.